Oh, we want it November the 7th. All right, finished work a little bit early today. So yesterday was too late, basically. I don't really have any any intention to work on this. So this is a problem. I should just cancel this. So I've done this before. It's a hard one. I can actually take a look. That's what I've done in the past, and it's a tough one. And I also don't remember exactly how this is done, but I thought about it as I was washing dishes yesterday. So I think with this need, okay, so first of all, it's a min-max problem. So a min-max problem, usually it is a binary search, right? So in this case, we just need a binary. So actually, no, I take it back. I don't think it's a binary search. So what happens is we need to calculate what is the current power for each city, right? That's what we need to know, the current power for each city. And once we do that, it is a binary search. So we calculate the current power. Actually, I think I have something from yesterday. Yeah. So like this is what we have, right? So this is the current power based on this range that we have for each city. And what we want, definitely the largest we can get is going to be 11, right? So if we can set 11, everybody will be 11. But we want the minimum to be maximum, right? So we need to raise 3 up to some number, but we don't know what that number is, right? We don't know what that number is. So we want to, and also you only have K. Yeah, you only have K more power stations you can add. So you can only add 2, right? You can only add 2. So we need to be strategic of where we want. So for example, 3, right? And you can set a goal, right? You can set a goal to raise the bar to that level. So in this case, the maximum is 11, the minimum is 3. So you take the middle, which is 7, right? So we said we want to set 7. So for each power station, right, for this one, if I want 7, so this one need to get 4. But you don't want to put 4 here because if you put 4 here, you're wasting things on the left. So what you want is to have the left range touch this, right? So left range, so this is 1. So given 1, we reach left 1, right 1. So this is the range. So you want to have the maximum range to reach here. So you have to add the power station here, right? You add the power station here, then you can reach this and can reach this. And that is what we are looking for, right? So we say I add 4, but of course we cannot do 4 because the most we can do is 2. So 4 is no good. So we lower it down, right? We lower it down to and not down. So it's a 7, right? So we'll lower it down. So the high will be 7, low will be 3. So now we do 5. 5 we can do. So we add 2 here. So now here is the difficult part, right? So we basically what happens? We have a range. We want to do a range add, right? We want to say from position 0, 0, 1, 0 to 2, add 2, right? And after we do that, we want to query, like we want to query this position, how much we added, right? So what's going to happen is we're going to have a range plus 2. We have another range of the same size, Maybe that can help us also. So like if a different size is even, maybe if it's the same size, there is some trick that we can do, but doesn't matter. Like this, we can make it +1, because each one like this is above 5, so we don't have to add. This, we don't have to add. We don't have to add. So if we need to add, like at a certain position, we need to add, then we need to get another range plus. So essentially, we're gonna have these ranges, right? And they have these pluses, and we want to know at a certain position, if we query, right? If we query a position, I want to know how much is being added to that position. It could be 0, could be 1, could be 2, could be a combination of them. So this requires some concept that I do know, which is, it's called a lazy propagation. Okay, I think it's called this. I think it's called a lazy propagation of a segment tree. Yes, this is, I think, segment tree. So what we need to do is we need to build a segment tree, and we will add this lazy propagation feature into it. I don't remember how this was done, but I thought about it yesterday, and I think what it can be done is we'll add another layer. It's called a cache layer. Okay, we'll do a cache layer. And the cache layer means if I do a range add of 0 to 2 plus 2, then the cache layer, it's essentially just a list, right? So the cache layer that represents this will get +2. I mean, of course, if you need to break it down, right, we'll get +2. But we don't apply to the actual segment tree. We don't apply it yet. We put it on the cache layer, and that's it. We just put on the cache layer. We don't drill all the way down to the bottom. We put on the cache layer, and we call it a day, right? And then when we do the query, right? When we do the query, so the cache layer can be, you know, any positions, but when we do the query, this is when we need to drill it down, right? This is when we need to drill it down. So basically, if we query a position, all the cache layer that's on that side, because it's gonna be like binary, right? The segment tree is gonna be binary. So if I have, let's just say, let's give an example, right? Give an example. If I have 0 to 10, okay, and I want to do a range add 0 to 10 plus 1, and this is the whole range. The cache layer will just say cache this node that you root, right? This node of +1. And then if I query, let's say I query 3, right? Now 3 is to the left half. So what we're gonna do is we will clear this layer, right? We'll clear this layer and we'll break it down. So query 3 is gonna be 0 to 5 and 6 to 10, right? So what happened is 6 to 10 will get this +1 because we cache, we like delete this one, but we put 1 here, and then that's it, right? We don't do it anymore. But now we gonna go here, right? 0 to 5, and then again we cache again, right? So this is gonna be 0 to 2 and 3 to 5. So this is +1, so +1 coming here, and this one actually just got rid of it, and then we have +1 bringing it down here. So this basically, we don't drill it down. We don't have to add every single one on this side. We don't add every single one on this side. We only add to this side. So with this one, it's gonna be 3 and 3. Now 3 and 4, and 5 and 5, right? So 5 and 5 will be +1. This will be +1. Now we drill it down 3 and 3, 4 and 4. So they all get +1. But essentially, we don't update all 10. We update 1, 2, 3, 4, 5. We're gonna update 5 nodes, right? That's drilled down. And when you drill down, actually it's not even a cache layer. It's just it's a segment tree, right? It's a segment tree, but we just don't put it down to every single one. We pause it here, right? We pause it here. That's what I think it means, right? That's what I think it means. That when you, because Regular segment tree is you will update, right? You will update, but instead of update of you will usually update a position, right? Update position. But here we're gonna update a range, right? We're gonna update a low to high. We're gonna update a range, but instead of updating everything in the range, you will stop wherever you need to stop, and then just don't keep going. And then you will query, just do a little bit more work in the query. So when you do query, if at the current node basically carries some number, you have to do a little bit more work to bring it down. So I think that's the idea, right? That's the idea. So you set a binary search on the top level, and then for every possible value, you just go through this. If it needs to add, you will add this range, right? And add this range and then keep going. If this is already bigger, you don't worry. If it's smaller, you query to see how much more can be added here. And then if it's not enough, we'll add more. So basically get a new range. So you just keep doing this. So the segment tree part will take log n, right? So this will be, I think, O n log n. No, it's actually O. N is because we have, so each one will take n log n, right? And overall will take another log n. So that is the binary search. This is the binary search part. This is to go through everything, and this is the segment tree. So this is how I think it's going to go. Of course, I don't know. I have to test it out. And actually, I'm very interested in solving this. I think it'll be fun, right? So we know kind of idea how to do this. We don't really know how to do this, but I have an idea of using two priority queue for this, but I kind of forgot how this one is set up. This one, we have an idea. We absolutely have an idea for this one, and I want to try it. This is TLE. No, I think this is yeah, this solution doesn't really work, but I do have an idea for this. I don't know which one you want to attack first. I think this one will be the simplest because I have the freshest mind. This one probably the hardest. I don't quite remember how I want to do it. This one I know it's a combination of two methods. I think we can do this one as well. This I don't remember. I have no idea. Absolutely no clue. So yeah, that's how the things are at the moment. Oh, we have another one. All right, I think this one probably is pretty simple. I think I'll C++. Given n, you must transform it into 0 using the following operation any number of times. Change the rightmost bit. Okay. Change the ith bit in the binary representation if the I minus 1th bit is set to 1 and I minus 2th bit through 0 bit are set to 0. Return the minimum. Okay, I don't even remember. I don't even understand what it's trying to say. Jesus. So you transform it into 0 using the following operations. Change the rightmost bit in the binary representation of n. So we'll change the rightmost, okay, and change the ith bit if the I minus 1th, that's to the right, I minus 1th bit is set to 1 and I minus 2 through to the 0 are set to 0. Return the minimum number of operations to transform. Okay, so n equals to 3, so basically it's 1, 1, 1. I'll change the rightmost, so this will become 1, 1. Why do you say 1, 1, 1? It's 1, 1. Right, so change the rightmost, so it'll be 1, 0, and then change the ith bit in the binary representation, if the I minus 1th bit is set to 1, I don't. With the second operation. Oh, I don't have to do it. Okay, with the second operation. So you can do either one. So you can change. So when you say, what do you mean by change? Change we can turn to 0 to 1 as well, right? Okay, so in this case I say, change the ith bit. If I minus 1 bit is 1, and everybody to the right is 0. 0's bit, so and then I change this, okay. So 6 is 110. I say change, so I need to turn these to 0. So change the ith bit if the I minus 1th bit is set to 1, and so I can do this, right? And then I cannot move because there's no throw. I need to change this into 1, and then this can change into this, and this can change into this. So I need to take 1, 2, 3, 4 steps, right? 4 steps. So we can actually back up. So the last step must be this, right? And then so to give it a number, so we have a bunch of, I don't know, right? So I need to turn this into 0. So what I need, I kind of remember this one, right? It's like how if they must have a leading one, right? How do you turn this leading one into 0? So this is not right. So your only way to do it is, if you want to change this, is if this one is a 1, right? So yeah, if you join change, so this one has to be a 1, and so this one only possible if it's like 0. So only if this is possible, then you can change this. Otherwise, you can never change this. So this problem becomes, I need to turn this into this. All right, turn this into this. And then once I turn this, and from here, I can say I can change this into 0. Then it becomes 0, 1, something, something, right? Can I change it to 0? And then I need to do this, but I don't. How do I do this? How do I? So I know. So I need to change this, but you have to change into this first. Yeah, I remember this problem. So how do you change this? That's just curious. How do you change this? How do you change this into 0, 0? So you will change into, we have this actually. We have to go 1, 0 to 1, 1. Everybody. And then to 0, 1, and then to 0, 0. So that's the path, right? Okay. So we basically know how these things work. How about this? Well, to do this, I to change the ith bit, right? To change the ith bit. So I cannot do anything at this moment, right? There's nothing I can do because I minus 1 is not. So the only thing I can do is, hello Rosiezy. The only thing I can do is change this into this, right? That's the only thing I changed the last bit. But if I do that, does it not help us? No, it does, because it says the ith bit can be changed if I minus 1. So like to the right is a 1, and so in this case I can change this into 1 1 1 because this is a 1, so I can change this. So now it's a 1 1 1. Next step is going to be I can change this. I actually cannot change this. No, I can, because this I can change because this is a 1, so I can change to 1 1 0. Right? This is a 1 1 0. This is the thing we already done. Right? 1 1 0. So 1 1 0 will change because now I can turn this into, so this will change it to 1 0. And then we go back to here. So 1 0 requires 1 2 3 steps. All right? This requires 3 steps to change. So this requires 3 steps. This requires 2 steps. This requires 1 step. This is 0 step, right? I think we just need to find a pattern here. A good pattern. So yeah, you go to 1 1 0, and then 1 1 0 is this. We already know because 1 1 0 is 3. So this is basically it's plus 3, right? This is basically plus 3. So oh yes, oh of course. You have no idea how soon I'm gonna do it.
Wow.
I'm gonna do it right now.
That's fine, I'm finished.
It'll take a while. It's like 3 hard problems I think this week. Maybe 2. Oh, and my back is so sore. From yesterday. Rude awakening. All right, we're back. So where are we? We're trying to find a pattern. We have a pattern here. All right, so we say 100. It's not 100. All right, so this is need 3 more steps. So this needs this needs 4, right? So this needs 5, 6, 7 steps, and that's essentially the same, right? That's 0, 0, 0, 1, 1, 1, and 1, 0. Let me just double check. This is what? 4. This is 5, 7. This is 6. So 7, 6, 5, 4. Okay. So that's it. That's everything, right? That's everything. Next thing is going to be this. So this essentially is we're gonna have to transform into this, right? That's just 1, right? And then basically this we're gonna transform so this essentially we're gonna go into this will do something into 1, 1, 0, 0, and then we'll follow this, right? And then we'll follow this because this will hit every single one in here, right? We'll hit every single one in here. Actually, no. Oh yeah. So this will hit here, hit 1, 1, 0, 0. The next step will be 1, 0, 0. Yeah, we do 1, 0, 0, and then the rest we already know. Okay, so basically we just need to find this whole path. All right, and this whole path will hit every single one of them. How do we get this path? Like, how do we get to 1, 0, 0? So like, how do you get to 1, 1, 0? So you go 0, 0 to 0, 1 to 1, 1 to 1, 0. Right? So from 0, 0, 0, you go to 0, 0, 0, 1. So essentially you'll do this path. So you'll have 0, 0, 0, 0, 0, 1, 0, 1, 1, and then 0, 1, 0, right? And then what? It can't go back, so you need to keep moving forward. Oh, you can change here. So now next you can turn into 110. Oh, you just turn back, huh? 110. Do this, do this, do this. That's how you get here. All right, you just this is the path. This is the path. So yeah, and then you get to 110, right? And then 110 will give you because you can change the last one, and then you can change the one, so you can change here, and then you can change this, right? You go so this way down, like 1 2 3 4 5 6 7, and then this way go up. It's exactly the same thing. It's exactly the same thing. So now you have this. So basically we go from 1 to this, right? From 1 to this, and then you'll just keep moving on. But how do we know from which position? So when you get to 100, that's gonna be 2 to the 1, 2, 3 minus 1, right? So we're going to 1 this is gonna be 2 to the 4th minus 1, because this is 7, and this takes 1 2 3 4 5 6 7 8, right? It takes like 1 2 3 4 5 6 7 8, and then from here you take 7. So yeah, so this is what we can find, right? This is what we can find. So the next thing is, if we're given a random stuff, right? If we're given a random stuff, let's say 1 0 1 1, okay, it's here. How do we know how many steps we need to take? So what we need to know is from here to 1 1 0 0, like how many steps do we need to take to get there? Or we can say how many steps it take from like this to go here, because we know from this to the end. So if I know from this to here, I can just do a minus, right? So how many steps I need to take from this to here? I don't know, because it's the same as from this to here, right? From this to here. So from this to here, so it doesn't really solve the problem. So from this to this, what will be the way to go about it? Okay. So if I have whatever stuff, right? And then what I need to know, because I know from this to 0 is going to be 2 to the, number of 0, right? Number of digits minus 1. So to go from here to 0, I just need to know from this to this, which is just from 0 to this 1 0 0 1 something. What is that? But 0 to this is the same as this way, right? So from this to this, so basically this is this, minus this. Okay, so I need to calculate this. Now to calculate this is essentially this thing minus this towards this. Now the picture gets clearer. Okay. What we need to do is do some substring stuff, and I think we can get this one done. Okay, this is actually not that bad. Take some time to find the pattern. Is it 8? Is what we're doing for 8? Yes, we're doing for 8. No, I think this is 8. I write something for. It is for 8. Interesting. Okay, so need to discover the pattern that this requires 2 to the 2 minus 1. This requires 2 to the 3 minus 1. Require 2 to the 4 minus 1. Right. So for any, this can be discovered by a trial and error. So for any given binary number, we can the answer is the number of steps from 1 to 0 minus the number of steps from 1b to Then the problem is transformed to how many steps from to 0, which we can solve in exactly the same way. Int, can we do int? Maybe. We need to do some bit manipulation, but I think it's fine. But essentially, I think it may be easier just to go with integer. Otherwise, you have to shift to left and right, and I think you might make mistakes. If I want to do this directly, I need to know the top bit. Right, I need to know how many bits there are. I need to know where the top bit is, which will be easier if we turn this into a string. Otherwise, how do you know the number of bits? So we count from right to left, and then Oh, come from right to left. Well, we can shift a number of times until it becomes 0, and that's how I know the number of bits. Okay, we know the number of bits. That will determine the number, the total count. And then I know the number of bits. I can just exclusive OR that. Right, I can exclusive OR that to get the remaining number, and then we just call it. Yeah, this actually is easier. Okay, so int, and then we say, we don't need this. Wait, do we need n? We do need n. So yeah, we do need n. And bits. Oh, can we count number of bits? Count number of, not 1 bit, total bits. Can we do that? Not really, not what I was thinking about. The bits, yeah, it's okay. So num bits. It's okay. So we say while nn, right? Num bits plus plus, and nn right shift equal to 1. So yeah, so number of bits are right shift once, right? So 1 bit, 2 bit, 3 bit, 4 bit, that becomes 0. Okay, so that's the number of bits, right? So when I know the number of bits, I can say total is going to be 1 left shift number of bits minus 1. This is the entirety, okay? This is the entirety. And then what we need to know is the remainder. So the remainder shall be n exclusive OR 1 left shift num bits. Actually, I'm not sure if it's left shift num bits, because if it's this, 3 bits, right? But I only want to shift 2 bits. Actually, it should be num bits minus 1. Okay, so this shall be num bits minus 1. Right, so exclusive OR, we will take away the top bits, so we have the remaining bits, right? Remaining bits. And then what we need to know is, hold on. Then we need to know is, so the remaining is the total remain. It should be minimum. We can actually call this function again. Minimum this, and we'll call it here, right? And then we shall return total minus, I call it remain. Okay. Okay, what if n is 0? Number of bits is 0. Total is 1 less shift to 0. Total is -1. And the remaining is, I don't know, I think this is going to be bad, so we should have a condition. If it's 0, we'll return 0. What if n is equal to 1? Okay, so yeah, we can actually try n equal to 1. Okay, if n equal to 1, so we have 1 bit. Okay, so total shall be 1, and then remaining is 1 exclusive or so num bits. We only have 1 bit. One left shift 1 is 1 left shift 0 is 1, right? Yes. So this is 0, so that's a 1, and 1 exclusive was 0, so it's 0. Okay, yeah, I think this looks about right. Okay, this one looks about right. Let's give this a run. See if it works. I press the wrong button. Press the wrong button. Unbelievable. Press the wrong button. Alright, so test case, yeah, we go 0, 1, and then actually 4, 5, 7. Let's do 1, 1, 0, 1, 0, 0, 1, 0, 0, 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so these are my test cases. Yep. Yeah, buddy. We got this time. Oh, we got it every single time. Oh, I think this is definitely much cleaner than the previous time. What else do we got? I think it's about similar. Nope, I like how I do it this time. And this is closer, I think, to what I was doing. Yeah, it's closer, but I just need to get the number of bits. I decided to do the number of bits. Well, I mean, technically, I don't need the total. I can just do this minus this, so these two lines can be saved. I just need these, but in Python it's much easier to get it this way. And I remember they have this gray code. Gray code. Yeah, it's some coding scheme, I don't remember. But anyway, that's that. Okay, that's that. I did pretty well in this one. I mean, it's a 70%.